So today's lecture is a review for our test 3, and this covers chapters 5 and 6 in Krane's Modern Physics. And chapter 5 covers the Schrodinger equation and solutions to the Schrodinger equation for potentials such as the infinite square well, the quantum harmonic oscillator, quantum tunneling. And chapter 6 covers the Rutherford scattering, the Bohr model of the atom, and some other details. So you first have to remember some ideas and concepts that were covered in our last test. And that first is the idea of wave-particle duality. So quantum particles can behave as both waves and particles. And the wavelength of these matter waves is described by the equation lambda is equal to h over p, where h is Planck's constant and p is the momentum. Now this is the wavelength of the wave packet, which we often describe with the symbol psi. Okay, so this is the wave function. Also remember the Heisenberg uncertainty principle. There's two forms of this. One of them is delta E, delta T is greater than or equal to h bar over 2, and then delta P, delta X is also greater than or equal to h bar over 2. Now remember that h bar is Planck's constant divided by 2 pi, and the h bar over 2 factor is because this is the minimum uncertainty. So this is the uncertainty which describes a Gaussian wave packet, and all other shapes of wave packets will have uncertainties larger than h bar over 2, and this is why the greater than or equal to exists in that equation. So the Schrodinger equation is the equation which describes non-relativistic particles. Now, we solved mainly forms for the time-independent Schrodinger equation because we solved for potentials that were constant in time. So this in one dimension is minus h bar squared divided by 2m, and then the second order spatial derivative of the wave function plus the potential energy times the wave function is equal to the energy of the particle times the wave function again. Now here m is the mass of the particle, u is of course the potential energy, psi is the wave function, and e is the energy. Now with the wave function, you can use it to find the probability of the particle's existence in certain regions of space. So if you want to find the probability of finding the particle in an arbitrary interval along the x-axis, say between a and b, then you integrate the absolute value of the wave function squared with respect to its spatial coordinate. Of course, this is also corresponding to the area under a curve of the probability density function, which is the absolute value of the wave function squared. And then if you want to find the probability that the particle exists in a very small region about some point, then you take the absolute value of the wave function times delta x, which would be the width of that region. Now the normalization condition is when you integrate the probability density over all possible values, that should give you 1, which means that the probability of the particle's existence somewhere is 1 or 100%. So the particle's somewhere. We're sure about that. Solutions to the Schrodinger equation, these wave functions have to satisfy certain conditions. The wave function itself must be continuous, and the first order derivative of the wave function also has to be continuous as long as you have finite values of potential energy. The wave function has to go to 0 as the spatial coordinate goes to plus or minus infinity. It can't blow up, in other words. It has to be normalized. It may be a complex function or a real function depending upon the system, and it must be single valued and defined at all points in space. You can use the wave function to find the average value of certain things. For example, the average value of the spatial coordinate, or the average position, would be the integral of x times the absolute value of the wave function squared with respect to the spatial coordinate, and that would give you the average position. If you have some other arbitrary function, g, say for example for general, and you want to know what the average value of it is, then you find that by taking the integral over all space of the complex conjugate of the wave function times g, and then times the wave function, and then you integrate that with respect to the spatial coordinate. It's very important if it's an arbitrary function to put g in between the complex conjugate and the wave function. Okay, it's very important to put it there because this operator g might not necessarily commute with the wave function. It might matter if you switch the order. Speaking of operators in which it's important that you keep the order correct, the momentum operator is a prime example of this. The Schrödinger equation actually suggests that we define the momentum operator in this way: minus I h bar times the partial derivative with respect to x. So that's our momentum operator. And then you see that if you take the expectation value of the momentum operator, that partial acts only on the wave function and not on the complex conjugate as well. The first potential that we solved using the Schrödinger equation was the particle in the infinite square well, often sometimes known as the particle in a box. For this potential, the potential energy is equal to 0 inside the well, which we defined as being between the x-coordinate 0 and x equal to L. So U is equal to 0 there. And then U goes to infinity at the boundaries of the well. So the solutions to this problem are the same as the solutions to a driven string, right? So if you pluck a string and you have the string fastened at either end, then the solutions to the particle in the box look just like the solutions to this problem. And so you have a series of standing waves formed. The ground state is a half wavelength bound. You can see by necessity the amplitude of the wave function has to go to 0 at the boundaries. And then the first excited state, you've got 2 humps there. Okay, so it's a full wavelength confined between 0 and L, and so on and so forth. Okay, so you can actually count the humps in your wave function and figure out where you are in terms of the energy level. If you've got 1 hump, you're in the ground state. If you've got 2 humps, you're in the first excited state. 3 humps, second excited state, and so on and so forth. Now, of course, the probability density is the absolute value of the wave function squared. So the wave function itself is pictured on the left here, and the probability density is pictured on the right. You can see that in terms of probability of a particle's location, for the ground state, the most likely place is at L over 2. For the first excited state, it would be L over 4 and 3L over 4, and so on and so forth. Remember that for all of these, the expectation value for the position is the average, okay, the average position, not the most likely. And so the average position for all of these energy levels would be in the middle of the well, because it's symmetric, it's a symmetric potential. If you're describing the energy levels for the particle in the box, those are h squared times n squared over 8mL squared, where h is Planck's constant, n is the energy level, which is a number that starts at 1 and goes up in integer steps from there. M is the mass of the particle, and L is the length of the box. Now you notice that these energy levels are not evenly spaced. They're proportional to n squared. Also remember that if you want a particle to jump between energy levels, then it has to either absorb or emit, depending on which direction it's going, the amount of energy that corresponds to the difference in energies between those levels. This is to conserve energy. In other words, a particle can't just jump up from the ground state to n equal to 3 without being provided energy, as that would violate conservation of energy. And so the energy of a photon that would cause it to jump from n equal to 1 to n equal to 3 has to be hf, which is then going to equal to the energy difference for these h squared over 8mL squared, and then that times 3 squared minus 1 squared. Okay, so that would be the delta E, which would give you the energy of the photon that would cause that jump. Likewise, if the particle jumps down from 3 to 1, then it's going to emit a photon of that energy. Okay? Now this is true not just for the particle in a box, but for a particle confined to any kind of quantum well. You have to have a photon absorbed or emitted that's equal to the energy difference between those wells. Now, if it's not a photon that causes the energy transition, for example, we talked about the Franck-Hertz experiment, in which that a collision with a particle and a transfer of kinetic energy in an inelastic collision can cause that same jump. But the amount of energy that it has to absorb still has to be discretized. It has to equal to the energy difference between the levels. Remember that the wavelengths are restricted to specific values for the particle in the box, and it's actually this formation of standing waves and certain only allowed values for the wavelength itself that causes everything else. The wavelength is equal to h over p, the momentum, and then the momentum is, causes the energy. P squared over 2m is the kinetic energy for U is equal to 0 inside the box, and those are your energy levels for the particle in the infinite square well. So lambda is equal to 2L over n for the particle in the infinite square well. And then the momentum values are therefore also restricted. P is equal to h over lambda, and if you solve for that, that would mean that P is equal to nh over 2L. Now remember that the average value for the momentum for a particle in a box is 0. And that's just because the particle spends as much time going right as it spends going left. And so the values of the momentum are actually plus or minus nh over 2L if you use the positive direction as, say, to the right, and the negative direction as to the left. The wave functions which describe the particle in the infinite square well are the square root of 2 over L times the sine of n pi x over L. Remember that sometimes we talk about the wave number k, and we would say the sine of kx, but the wave number in this case would just be n pi over L. We also studied this potential in 3 dimensions, and remember that this introduced the idea of degeneracy. The definition of degeneracy is when different sets of quantum numbers, or different wave functions, result in the same energy for that particle. So in 3 dimensions, for example, the wave function for the particle in an infinite rectangular solid, I guess, would be a times the sine of n1 pi x over L1 times sine of n2 pi y over L2 times the sine of n3 pi z over L3. Okay, the dimensions don't have to be the same in each direction. In other words, it doesn't have to be a cube. All right? So your energy levels for this would be pi squared h bar squared over 2m times n1 squared over L1 squared plus n2 squared over L2 squared plus n3 squared over L3 squared. So those are your energies. Now the degeneracy happens like this. Let's say that we do have a cube, for example, and L1 equals L2 equals L3, and I'll just call them all L. Okay? In the ground state, N1, N2, and N3, or Nx, Ny, and Nz, would all be equal to 1. Okay? Now, if you go up to the first excited state, you could have a combination of quantum numbers like N1, N2, and N3 respectively being 2, 1, 1, or 1, 2, 1, or 1, 1, 2. Now, those would all give the same value for the energy. And that value that they would give is 6 pi squared h bar squared over 2ml squared. But those are different, distinct combination of quantum numbers. And so the first excited state has a degeneracy that's threefold. Okay, that's how we use that idea. The nomenclature is degeneracy is threefold. Moving on to the finite potential well, here's a graphical picture of what they look like. Remember that because the potential doesn't go to infinity at the boundaries for a finite potential well, instead, inside the well the potential is 0 and outside the potential is some constant value that stretches on to infinity. Basically what that means is that the solutions to the Schrodinger equation outside the well are decaying exponentials. Okay? So what that means is that the particle can actually penetrate into the side of the well. The wave function is non-zero outside the well, which means that the wave function squared is non-zero outside the well, which means that there is a finite probability that the particle exists outside the well, even if the energy of the particle is less than the potential barrier energy. Okay? Now this would be forbidden classically, but in terms of quantum mechanics, there is a finite probability that that particle will be able to tunnel into the well. Now, if you compare the infinite potential well solutions to the finite potential well solutions, that means that for wells that are the same length, say that they're both equal to L, that the wavelength for the finite potential well is longer. If the wavelength is longer, then that means the momentum is different as well. It's smaller, which means that the energy levels are going to be compressed. Okay? It also means that for the finite square well, the particle can actually escape. If the particle is bound with some energy E, and you give it enough energy so that its energy exceeds the barrier of the well, then it can escape the well and be a free particle. Now, although an exponential decay, which is what happens when it hits the barrier of the well, although that doesn't have a sharp ending point, sometimes we can use a parameter that measures about how far that wave function extends past the classical turning point and buries into the well. We call this parameter in our textbook eta, okay? And it's known as the penetration distance. And eta is equal to h bar divided by the square root of 2m times u naught minus e. So you can figure out about how far the particle went into the well. The next potential we studied was the harmonic oscillator potential. For the test, I'm not going to require you to know the wave functions for the various energy levels with the harmonic oscillator. I'll provide those to you if you need them, okay? But I'm not going to give you the energy level values. Okay? And I'm not going to tell you what the potential is or how to solve for the angular frequency or anything like that. So you're required to know that. So remember that for a mass on a spring, that F is equal to minus kx, where k is the spring constant and x is the displacement of the particle from its equilibrium position. The potential energy for a mass on a spring is 1/2 kx squared. When you solve the Schrodinger equation for this potential, it gives you energy levels that look like n plus 1/2 times hf, where f is the frequency of oscillation. You could also write it as n plus 1/2 times h bar omega. Now, omega squared, the angular frequency, is equal to k over m, where k is the spring constant and m is the mass of the particle. Remember that the frequency is 1 over the period, which is omega over 2 pi. So that's how the frequency, the period, and the angular frequency are related. This is what the energy levels for the harmonic oscillator look like. They're evenly spaced. Because E is equal to n plus 1/2 times h bar omega, then the delta E in between each energy level is just h bar omega. And you can see that it starts out at a non-zero value of 1/2 h bar omega and goes up from there. One of the things that students get the most confused about is that the energy levels for the harmonic oscillator don't start at n equal to 1. They start at n equal to 0. The reason for that is just that when you solve the Schrodinger equation for the potential 1/2 kx squared, that the solutions are inside the well, the Hermite polynomials, and these are parameterized by a quantum number n, which starts at 0 and goes up from there. So it's simply the solution to the Schrodinger equation which gives us our quantum numbers, and for the harmonic oscillator those start at 0. So don't get confused about that, because for every other potential system that we studied that appears on this test, the Bohr Model, the hydrogen atom, the infinite square well, so on and so forth, for all those n starts at 1. So don't let that confuse you. Now I'd like to bring up the fact, I didn't emphasize this before for the infinite square well, but I'll emphasize it here, that in your ground state you still have a finite amount of energy. And that's kind of a quantum sort of idea. It's not a classical idea. It would imply that at absolute 0, for example, your particle is not still. It's still oscillating around, it still has a momentum, and it still has a kinetic energy associated with it. Okay? So this is known as the 0-point energy for a particle. This is what the quantum solutions to the harmonic oscillator look like. Note that you can still count the humps and figure out what energy level you're at. So here's a plot of the probability density function. The wave function is shown in blue here, and the classical turning points where it meets the boundary of the well are shown by these vertical dashed lines. So you can see that the ground state has 1 hump, the first excited state has 2 humps, second excited state 3 humps, and so on and so forth. So you can still count. And note for the harmonic oscillator potential, you still have tunneling into the barrier, okay? Just like you did with the finite well. And that's because the value of the potential at the classical turning point is finite and not infinite. Now finally, we studied quantum tunneling on square barriers like steps and then little mesas. Classically, this is forbidden, but in terms of the quantum mechanics, we can solve for the probabilities of reflection and transmission, which we called R and T. And remember, when you have particles incident on a barrier, there's only 2 possibilities. It can be reflected or transmitted. And so that means that if you sum up the probabilities of reflection and transmission, you should get 1. Now we're going to talk about the solution where the energy of the particle is less than the potential energy of the barrier. E is less than V. And those solutions are shown next. So this is what it looks like. You have a wave incident on the barrier, which is defined as having some width L, where the beginning of the barrier starts at x equal to 0 and it stops at x equal to L. The potential is 0 outside of the barrier, okay? And inside the barrier, the potential is equal to some finite amount, okay? Now, I'm going to give you the equation that's an approximate value for the transmission. This is the same equation that they often use in the physics GRE to solve for these things in the textbooks that you'll see in the review sessions for the physics GRE. And that's that the transmission coefficient is approximately equal to e to the minus 2 kappa L, where L is of course the width of the barrier and kappa is equal to the square root of 2m times the potential minus the energy of the particle divided by h bar. The square root doesn't extend to cover the h bar on the denominator, okay? It's only on the numerator. Moving on to chapter 6, the first thing that we covered was the Rutherford gold foil experiment. This was the most famous collision experiment in history. So basically what happened was, in this experiment, they had a source of alpha particles, which are just helium nuclei, and they passed them through some slits to collimate them, or some pinholes, and they accelerated them through a voltage. And then they were incident upon a gold foil target, and the gold foil was very thin. It was on the order of 600 nanometers or so thick. And then what happened was, quite surprising, the alpha particles were actually reflected back by the target. And they could see that, although a small percentage of the time this only occurred, that it did happen that the particles were sometimes reflected straight back. And remember that Rutherford likened this to a 15-inch shell penetrating a piece of tissue paper. That's how unlikely it seemed, because the foil target was so thin. So the equations describing this he came up with to explain the scattering event. First of all, he defined what's known as the impact parameter. In our textbook, we use B to symbolize the impact parameter. Okay? And the impact parameter is equal to Z1 times Z2 times E squared divided by 8 pi epsilon naught times K times the cotangent of theta over 2. Now, each one of those things, Z1 and Z2 are the atomic numbers of the projectile and the target nuclei, respectively. So basically, you're multiplying the product of the charges of the two nuclei there. And you're dividing by 8 pi epsilon naught, where epsilon naught is the permittivity of free space, 8.854 times 10 to the minus 12. And then K is the kinetic energy of the incident particle, in this case the alpha particles. And theta is the angle of scattering. Okay? Now, B, the impact parameter, is also the effective radius of your target nucleus. Because there's a very, very strong force in between the two nuclei, the Coulomb force, they don't ever actually touch. This isn't hard sphere scattering. Okay? So beta is the distance off center from the center of the alpha particle to the center of the target nucleus. It's how far off the two centers are. And it gives you an effective nuclear size, as if the two particles underwent hard sphere scattering. So that means that the cross-section, which is the cross-sectional area that the incident particle sees for the target nucleus, is equal to pi b squared. Now, the probability of the particle being scattered in this equation is shown as the fraction, or f, and that's equal to nt pi b squared. Pi b squared, yet again, is the cross-section for scattering, sigma. T is the thickness of the target, and n is the density of the target nuclei, or the number of nuclei per unit volume. We also discussed hydrogen spectra specifically, but emission spectra in general act like fingerprints. So if you take a gas and you excite it, it's going to emit not a continuous light, not white light, but light of very discrete, distinct wavelengths. And some of those are shown here for hydrogen, mercury, and neon. Now, they're different for every single atom, and that's why I said it acts like a fingerprint for the identification of what kind of gas you've got. This was studied in the late 1800s, and Balmer was the first one to come up with a nice equation describing them. I'm not showing his form here. Instead, I'm showing Rydberg's version of the equation. And that is 1 over lambda is equal to the Rydberg constant times 1 over 2 squared minus 1 over n squared, where n is an integer that starts at 3 and goes up in steps from there. The Rydberg constant is 1.097 times 10 to the 7th inverse meters. So that describes the equation. It describes what the wavelengths in the visible spectrum that were seen by Balmer. Now, there were also hydrogen series in the ultraviolet, and that was the Lyman series, and in the infrared, the Paschen, the Brackett, and the Pfund series. The equations describing them are shown here. Basically, you've got 1 over lambda times the Rydberg constant, and then times 1 over an integer squared minus 1 over n squared. Now, which integer that is depends upon what version or what range of the spectrum you're looking at. For the Lyman series, it's 1 over 1 squared. For the Paschen, 1 over 3 squared. The Brackett, 1 over 4 squared. And the Pfund, 1 over 5 squared. And then for each one of those equations, you start at 1 larger than your first number and go up from there. So for the Lyman series, it's for n greater than 2, the Paschen, n greater than or equal to 4, and so on and so forth. All right? Now, they understood that these equations described the spectrum from hydrogen, but they didn't really know the physics behind that, okay? And it took Bohr to come up with a model of the atom that successfully described it. We now know Bohr's model to be incorrect. It doesn't describe fine splitting of spectral lines. It doesn't work for atoms other than hydrogen or singly, only ones with single electrons and so on and so forth. There's many problems with it. But it still does a nice job of conceptually explaining to students what's going on. It's a semi-classical model and easy to visualize, and that's why we still teach it. So Bohr's model of the atom starts off with the idea that the centripetal force that the electron experiences in its orbit around the nucleus is provided by the Coulomb attraction between the nucleus and the electron. So for a hydrogen atom, that's mv squared over r is equal to 1 over 4 pi epsilon naught times e squared over r squared. Now Bohr went on further to say, look, the electron, since it's an accelerating charged particle, should theoretically radiate away all its energy and crash into the nucleus. But it doesn't do that for certain radii. The radii that does not happen for are the ones where the angular momentum of the electron is quantized. Specifically, mvr is equal to n times h bar. Okay? Now he didn't really provide a very compelling explanation as to why this happened, but he did describe an equation that sort of that parameterized it. Now, if you use the equation for the force and for the quantization of the angular momentum, you can then solve for the radii, the allowed radii, where it won't spiral in and crash into the nucleus. And those values are n squared h bar squared over mk e squared, where k here is the Coulomb constant, 8.99 times 10 to the 9th. M is the mass of the electron, h bar is Planck's constant divided by 2 pi, and E is the fundamental charge. So if you solve for those things, it's n squared times a constant. And if you solve for what that constant is, it's 5.3 times 10 to the minus 11 meters. And this is known as the Bohr radius and is often symbolized with A naught. Now if you use that quantized value for what the radii are allowed to be, that quantizes the energy. If you solve for what the energy of any orbit is, it ends up being minus 13.6 electron volts divided by n squared. So those are the allowed energy levels for the hydrogen atom. Now, these allowed energy levels completely explain the hydrogen spectrum. All of those spectra were basically just electrons hopping between the various discretized energy levels. Okay? And all of the quantized wavelengths then made sense in terms of the various hydrogen spectra. For example, the Lyman series was an electron being in an excited state and then transitioning back into the n equal to 1 state. The Balmer series was an electron being in an excited state and transitioning back into the n equal to 2 state, and so on and so forth. And so Bohr's model was considered a great success, although even at the time they knew that it had limits and that there was some other truth that they needed to find. You can extend the Bohr model to other atoms. Bohr did this. You can extend it to atoms other than hydrogen as long as you've only got one electron in that atom. Okay? So as long as it's ionized. In that case, the radius would be equal to n squared times A naught divided by Z, where Z is the atomic number of the element. Now, in this case, this makes sense, right? The radius is going to be smaller for elements larger than hydrogen. And that's just because the Coulomb attraction in between that really large, highly charged nucleus and that single electron is going to be stronger because the product of the two charges is stronger. So it holds it more tightly and it's closer. Okay? That also makes the binding energy higher. Okay? It's bound more tightly. In other words, the well is deeper. So the energy levels for something other than hydrogen would be minus 13.6 eV times Z squared over N squared. Yet again, Z is the atomic number here. Those constants that I show on the slide, minus K E squared over 2A naught, okay, those are all just the constants that multiply through to make the 13.6 eV. You can check me out if you don't mind. K there is the Coulomb constant, 8.99 times 10 to the 9th. I know we've got a lot of K's and it can be frustrating. You can also extend it to other atoms and refine your values of the energy and the radii by calculating what's known as the reduced mass. And this idea says that if you have a nucleus and an electron, it's not really, if you're being technical about it, the electron orbiting the nucleus. In fact, both the electron and the nucleus are orbiting their center of mass. So this is a small correction, okay, for most elements, right? And that's because the nuclear mass is so large compared to the electron mass that the center of mass and the nucleus are super close together. So the correction is small. The reduced mass mu is the mass of the electron divided by 1 plus the mass of the electron divided by the mass of the nucleus. Here I call the mass of the electron little m and the mass of the nucleus big M. Okay? And you can see that since the mass of the electron is about 1,000 times smaller than the mass of the nucleus, basically the reduced mass is very close to the electron mass. But if you have a different kind of atom, let's say that you have something like positronium, where you have an electron and a positron orbiting their common center of mass, well then that would reduce the reduced mass would go to 1/2 of the electron mass. Okay? So if you have something other than electrons orbiting big fat nuclei, then this reduced mass correction becomes more important. Now, the Bohr model of the atom was validated by the hydrogen spectra, but it was also validated by the Franck-Hertz experiment. And Franck and Hertz studied the phenomena of ionization. So what they did was they had inside of a vacuum tube mercury vapor, a rarefied mercury vapor. And then they had a filament which supplied electrons that they accelerated across the mercury vapor by applying a voltage. Now what happened was, the conclusion of this experiment was, that the electrons, when they were accelerated and have enough energy, would undergo inelastic collisions with the mercury atoms. These inelastic collisions would transfer the kinetic energy from the electrons to the mercury atom, and that energy would be used to excite electrons within the mercury from the ground state to the first excited state. Okay? That was a defined set amount of energy. And so if you measured the current output of the electrons traveling from the filament across to the collector, you could see dips, okay? And these dips corresponded to the electrons there transferring almost all of their kinetic energy over to the mercury atoms. And then they didn't have enough kinetic energy left to make it through to the collector, and so the current went through a drop, okay? And that happened at multiples of the energy difference between the ground state and the first excited state at 4.88 eV. So if you see the dip at 4.88 eV, that means that it went through one collision and transferred almost all of its energy. But then, if you dial the kinetic energy of the electrons up more to say 10 eV or so, well then it can go through 2 inelastic collisions and get rid of almost all of its energy, and you'll see another dip, and so on and so forth. Okay? Finally, we covered X-ray spectra. Now, in a previous test, we covered bremsstrahlung, or braking radiation. And that has a continuous spectrum that starts at the cutoff wavelength and then goes up from there. However, on top of this continuous spectrum, which is like a hump with a slowly decaying end to it, you also have these very strong, high-intensity, narrow peaks. And these are called characteristic X-rays. Now, different elements have different energies of X-rays. Moseley studied these characteristic X-rays, and he found some equations. The energy of the K alpha X-ray is equal to 13.6 eV times 3/4 times Z minus 1 squared. And then the energy of the L alpha X-ray, HF L alpha, is equal to 13.6 eV times 5/36 times Z minus 7.4 quantity squared. Now first let me explain the difference between the K and the L X-rays. The K X-rays are created when you have, for example, an electron beam bombarding your target. The electron then knocks an electron within the target material loose that's in the ground state, that n equal to 1 state. It knocks it loose. And then one of the higher energy level electrons within the target atom falls in to fill that vacancy. That's a K alpha X-ray. That's a K X-ray. And the K alpha is when it makes a 2 to 1 transition. Okay? Now the L alpha X-ray is when the electron that gets knocked loose is equal to the n equal to 2 state. And then an electron falls from n equal to 3 to n equal to 2 to fill that vacancy. That's L alpha. Okay, so that's the nomenclature. Now the equations were described by the fact that although the Bohr model doesn't do a perfect job of describing multi-electron atoms, there are some approximations that you can make. Okay? So those approximations are that if you have an electron and it's sitting not right next to the nucleus but some distance away, so that there's electrons in between one of the outer shell electrons and the nucleus, it's got a screening effect. if you remember Gauss's law from introductory physics, right, the electric field that's seen by something is equal to the total enclosed charge, okay? And so since the nuclear charge is effectively screened by those inner shell electrons, that explains these factors of 3/4 and 5/36 in there, and it also explains why you subtract a little bit off of the nuclear charge, okay? So Moseley obtained this data by taking X-ray spectra for a bunch of different targets, mostly metals, and then doing a plot and a linear fit to that data for the K-alpha and the L-alpha X-rays. It was considered a validation of Bohr's model of the atom because it showed that the energies of those X-rays were still proportional to Z squared, and that was considered a triumph. All right, so that's everything that we covered for test 2. If you have any questions, don't hesitate to ask, and I'm always available if you need to knock on my door. Thanks.